Hi everyone. How's everyone doing? You have fun? Hey, can I hear it? Like, can you give me some? That's cool. Okay, so now the fun stops. We'll be talking about change detection Angular 2, and this is probably a bit technical, so I try to make it fun. No, I think it's gonna be fun. It's actually really, really cool. So, yeah, my name is Pascal. You can find me on Twitter with that Twitter handle over there, just my name. There's also the hashtag. If you want to tweet something today, just use that hashtag so everyone can follow. Right, so I spent the last couple of weeks trying to understand change detection in Angular 2, like how it works and what's going on and what we can do with it and you know how powerful it is. And today I would like to show you my learnings, and yeah, I think it can be really cool because it's really powerful, and I hope it helps you to understand how it works and how you can take advantage of it when you build your own Angular 2 application. Right, so there's an Ask Me Anything session afterwards, so there will be question afterwards. I actually have to check where it is. I don't know yet, but just that you know. I think we can just get started now. So change detection. What is change detection? So it turns out change detection is a term that basically describes a very basic task. And the task is simply taking the internal state of an application and kind of like trying to make it visible in some user interface, right? So what we see here is a model, and that's our state of our application. And a model can basically anything, right? And JavaScript especially. We can have like objects and arrays, and we can even have references to other objects. So we can have parts of our model that kind of point to different parts of our model. That's why we have these different connections here in the slides. Right, so we have those data structures in JavaScript, and we want to make them visible somewhere. And usually those things that we have as structures, they might end up somewhere as maybe buttons or paragraphs or links when we do web development. And this thing, we call that DOM, right? The document object model. This is where things end up. The thing that is basically that makes it visible to the user in the browser. And so we call this process basically rendering, right? So we take some input, which is the data structure, and then we generate some output with the DOM, and then we have some, something that we can see. So it's actually a very, very simple task, right? It's like it could be like one function. It takes an input and it generates an output, and then we make that state visible somehow. And it turns out that this kind of simple task, it gets quite tricky as soon as we want to track changes over time, right? So once we do it initially, it's all right. But then if we have a change that happens somewhere in our application, and that could happen due to different things, like, for example, the user interacts with the UI, or there's a server that returns some data to our application, which then, again, changes the state. This basically causes some change somewhere in our model, and we want to reflect that back in the DOM again, right? And when we access the DOM access is pretty expensive, right? So we want to try to keep that low, and we have to optimize here. And so the tricky part is really like to identify where is the change in our model, like what is the change that happened, and where do we actually need to update the DOM without like spending too much time on it. And it turns out that there are different ways to handle that. You can have a server-side solution that basically re-renders the page when there's like someone clicks on a link, right? And then you make a request and you get a new response. It's like it's not really change detection in that sense, but you have a change that might happen, and then you give the result back to the user. And there's virtual DOM, like the thing that React uses, and there are many different other ways to handle that. So bottom line is that change detection is basically like the goal is to project the data of our application into the user interface. And there's a great article that kind of touches on the different ways to do that by Tero. I think he's in this room over there. That's Tero. So he wrote an article called "Change and Its Detection" in JavaScript frameworks. So it gives you a kind of overview of how different frameworks deal with that kind of problem. Okay, so now that we know what change detection basically is all about, like what we want to achieve, let's talk about the thing that basically causes change. Like, what is it that causes change in our application? Because it turns out that this is very important, right? We have to understand when we want to detect change. So, and to get started, I would like to take a look at this component template here. This is an Angular 2 component template. And it's actually very, very simple. There's nothing special going on, right? We have a first name and a last name, 2 expressions. So apparently we have those properties on our component, right? Because the data always comes from the component into the view. It's like always that way. And then we have a button that has this event handler, change name. So apparently when this button is clicked, change name is being executed, whatever that particular method does. Let's take a look at the code of the component. It's a bit simplified, so you can see that the component decorator doesn't have all these options. You can imagine them now. So I just want to point out that this thing is not just a class, it's a component. We actually see those properties here. And then there's this change method, change name method, which basically does nothing but just changing the first name and the last name. So whenever that button is clicked in the view, we basically change the application state, right? So this is change in our application state. The moment we click that button and the moment that this particular handler is executed. Another scenario would be this one, right? So we have a context application, and this particular application has a list of contacts. It's initially empty. And once this component initializes, we basically fetch data, our contact data, from a remote server, and then update this context property so that we get this update in the view as soon as the data returns, right? Again, this is the moment when application state has changed. We're changing the property of this component, and we want to display that particular change in our view, like in the UI, right? That the user sees it. Okay, so all in all, we basically have 3 things, if we kind of summarize it, that can cause change. That is events, right? Like click or submit or whatever. AJAX requests, using XHR, or even in JavaScript timers, right? Set timeout and set interval, like these kind of things. And it turns out that all these 3 things, they have one thing in common, and it is that they're asynchronous, right? So basically, whenever something asynchronous happens, it can be that application state has changed. So now that we know what can change application state, and that this is the moment when we want to update the view, if we think of Angular, you might wonder, what is it that basically tells Angular, hey, there is this button that has been clicked, you now have to update the view, right? There has to be some mechanism that tells Angular to update that view. So what is it that notifies Angular? Since it's Angular, I think it's quite obvious, right? It's some sort of magic, right? It has to be magic. I'm just kidding. It's zones. So there's this feature called zones, which is not part of JavaScript. Actually, it has been proposed at TC 39, so we might get it sometime soon. But for now, it's just a feature that we have to understand, and then we know what's going on. But before we actually can talk about what zones are, we have to take one step back and understand JavaScript first, right? So let's do that. So I would like to take you on a little journey and explain you what basically happens when we execute a JavaScript program, and then also what happens when we have asynchronicity going on and how that affects our application. So what we see here is a simple program. It doesn't do anything special, right? It's just 3 functions, foo, bar, and bazinga. And when this code is being executed, we call bazinga, which then calls bar, and then foo, and so on. So JavaScript is single-threaded, right? Which means it can basically just do one thing at a time, right? So just one code snippet at a time. And that's why we have a single call stack, right? And the call stack is the thing that basically keeps track of where we are in our program. So assuming that we would execute that code, this is basically what happens. So first of all, the script itself gets executed. It's like the sort of main function, right? And then the JavaScript VM basically sees all these the function declarations, and then at some point there's this Bazinga call, which kind of executes the actual program, right? So, and this is what happens to the call stack. We have this main function that is being pushed to the call stack. Then Bazinga is being called, so it gets pushed to the call stack. Bazinga calls bar before it returns. So bar is being pushed to the call stack. And so on and so forth. Bar calls foo, and once foo is done, it returns to bar, and then we pop it off of the stack, and then we return from bar to Bazinga. And then once Bazinga is done, the program is done, right? So you now might think, okay, well, awesome, that's like single-threaded call stack, like nothing special going on here. So like, why is that important? Well, it turns out that it gets a bit more interesting if we take a look at asynchronicity. So what happens when we have asynchronous code? Because JavaScript, right? In JavaScript, we do have asynchronous code. So when we write asynchronous code, we have a bit more, more things involved when this code is being executed. So what you see here is, again, on the left-hand side, we see our program. It's, again, just a function foo. We do a set timeout of, in this case, 0, but it can be anything. It can be 5 seconds or whatever. And then we call bar, right? We, again, have our stack, our call stack. But then there's this other thing called web APIs. And web APIs is basically something that is not part of the VM. It's something that is provided by the browser. So things like set timeout or at event listener, like these kind of APIs, those are provided by the browser. If you write Node.js code, it's probably some sort of C++ implementation that you can make calls to, but you have a kind of equivalent to that. So now, and then there's this task queue and this event loop. And I'm going to touch on that in a second. But for now, let's just start understanding what's going on here. So again, we execute that program, which is the main function, right? Then we execute foo. Foo is done. And then we execute set timeout. Now, set timeout comes with a callback that is being executed once the set timeout is done, right? So, and this is where web APIs come into play. So the web APIs, basically, they schedule that timer. And then once that timer is done, something weird happens. But for now, set timeout is being executed. This callback is scheduled somewhere, and then the function returns. That's it, right? And then the main function is done. Boom. Once bar is executed. Okay, so that was basically the first run, synchronous. So now this callback is hanging there, and at some point, we can't just the web API can't just notify randomly that this function has been executed, and that we can it can change our application state. So basically what happens is once that web API call that is hanging there is done, we have to push it to the task queue, right? This is, or we don't have to do it, but the web API does it for us. So it's a queue that basically, it queues up all these tasks that are asynchronous, and once there's time, these tasks are going to be picked up by the event loop. So that's what the event loop is. It's this very, very tiny part that basically takes care of, so it basically tracks if the call stack is free, right? If there's nothing in the call stack anymore, it basically pulls the next task from the task queue and puts it into the stack so it gets executed, right? So this is what happens, and we call this also the next tick, okay? So whenever you do a set timeout of 0, you basically defer that execution of that callback to the next time the call stack is clear. Okay, so now we know how that works. And actually, what you've seen so far was basically a ripoff of Philip Roberts' talk, What the Heck is the Event Loop Anyway? And I highly recommend you watching that talk. It goes into a bit more detail. So, but why is that important? Like, why do we want to know it? Well, it turns out that this is exactly the same thing that happens in Angular, right? This asynchronicity, this, the moments when application state can change, when you click a button, when you do a set timeout. So there has to be something that triggers Angular and tells them, we have to update the view. And this is where zones come into play, because zones, they allow us to basically perform an operation each time a task is being entered or exited. So what does that mean? Well, so let's take a look at that code again. We have foo, we have the set timeout call, and then we have bar, right? In order to execute that code in a zone, we can use something like zones.js, which is a library developed by Brian Ford from the Angular team to kind of bring that zones feature to JavaScript. You have zones in other languages like, actually it's a feature from Dart, you have it there by default, and Brian kind of ported that functionality to JavaScript, which is cool. So to run this code in a zone, this is what you have to do. You call zone.run, and as you do this, whatever is executed in this run block is basically a task. Right? I'm not talking about a task from the task queue, I'm talking about a task from the perspective of a zone. So it executes that code, there's nothing special going on, but what we don't see here at this point is that, so what zone does, it basically monkey patches a lot of asynchronous APIs that we have in the browser, so it can hook into them. So this setTimeout call here is actually not the global setTimeout, not the native one. We're actually calling zone.setTimeout, and that one will delegate it to the native call. Why does it do it? Well, because it kind of wraps some hooks around it that don't do anything by default. It's basically no operations. So this code executes just normally. But all of a sudden, we have actually the benefit to kind of extend this zone and hook into these tasks. And then we know when these tasks are being executed and when they're done. So in fact, what happens is that this setTimeout call creates another inner zone, like a child zone, which is then also just simply a task that is being executed. So again, zones can be extended. Like you can have zones APIs like before task, after task. There are other things that you can extend. And so you can see here, if you want to take advantage of this, if you want to define some hooks yourself, you have to fork a zone, right? You kind of extend the existing one. Your child zone inherits from your parent zone. But the moment you define these hooks, those are available to that zone. So the zone will basically execute these hooks automatically for you without you doing anything special in your code that is being executed. Okay, so now why is that interesting? Well, it turns out that Angular takes advantage of exactly that. Right? That's why we can write code that is just, it looks like it is simple JavaScript code. It's just JavaScript code. There's nothing special that we have to do to notify Angular because Angular notifies itself using zones. In fact, it has its own forked zone called NG-zone. And that thing is a bit special because it extends the API a little bit. There are some calls, some APIs called onTurnStart and onTurnDone. They're both based on observables. And there are some more. But those are the ones that are interesting because if we take a look at the source code of Angular 2, the actual source that makes it happen, that automatically a change detection is being performed and the update, the view gets updated, is actually just a couple of lines of code. So this is essentially what happens. Angular accesses its own zone instance, the NG-zone. It subscribes to the onTurnDone event, which is the event that is being executed once a turn is done, which is basically a task, something like setTimeout or an event listener, right? And once that is being fired, it executes something called tick in the same zone, right? Now tick is simply this function here. It calls detect changes on all change detectors in this application. I'm going to explain in a second what that means, but for now, just keep that in mind. If you wonder what it is, what updates the view, what triggers Angular to update the view, it's just that. It just uses the power of zones. It extends this the global zone, and then basically just runs this simple function. That's all that happens. Okay, so if you want to learn more about zones and stuff, there are 2 articles that I wrote on our blog. There are links in these slides. You can actually click them. So when you take a look at those slides on your own machine, you can actually read those articles. Okay, let's jump right into change detection. Okay, change detection in Angular 2 is, let's say, a bit complex, but it's totally doable. So let's say we have this component tree, right? An Angular 2 application is always a tree of components. You have a root component that is being bootstrapped, and then you have some child components in it. The first thing we need to realize is that every component has its own change detector, right? There is one mechanism that kind of triggers change detection, but still every component gets its own change detector, which turns out to be a very powerful thing. because it allows us to decide individually what we want to do with each component when change detection is being performed. Okay, so let's say this is our application. We don't really bother for now what this application does, right? It's just important to know we have this tree. Now, somewhere in this application, during the runtime, there's an event happening. Maybe we click this button that we've seen earlier. Now, when this button is clicked, this event is being fired, which again triggers the onTurnDone emit, which Angular is subscribing to, and then tick is being executed. And this kicks that basically makes change detection kicks in. And change detection always performs from top to bottom. So we start at root, and then it goes all the way down for each component, right? So that's the second thing we need to realize. The data always flows from top to bottom. Change detection is always performed from top to bottom, always from root. There are no cycles, and it's always that the component basically updates its view. It's a directed tree. It's a single flow, an unidirectional flow. Sorry. The second nice thing here is that change detection in Angular 2 gets stable after a single pass. So there's no digest or anything, right? So when this thing is executed and your model doesn't get stable after the first pass, you actually get an error because you're not allowed to have side effects, which is also pretty cool. So that makes it basically way more predictable for us. I do have a demo on that, and I want to show it really quick because actually I have really cool demos for this talk. So the first one is not super duper exciting, but I just want to show you that the stuff that I'm explaining here is actually true. So what you see here is a component tree, and each of these components is an Angular 2 component. When I refresh this page, you will see that Angular will trigger change detection for the entire application. This is what it does initially, right? And you can see that it runs change detection for a component when it turns green. So I'm going to refresh the page, and you'll see they're green, and then turn blue again, right? I can even click this button here, trigger change detection, which just fires an event, which again, causes zone to trigger its own event, and then change detection is being executed. So I click this button here, and we'll see that it doesn't work. So there is apparently a bug in this demo. Yay! Alrighty, okay, let's refresh once again. And there it is. I can take a look at the source code for a second. And I was so well prepared. Alrighty. Okay, I think I know what it is. I'm going to return this one. Okay, this is going to reload, and I hope I fixed it. Click this button. Yay, it works. Of course, that was totally planned. No, it wasn't. Live coding works on stage. Okay, so I click this button, and you can see everything turns green. Okay, it performs change detection. Nice. Okay, back to slides. Boom. So now the big question is now, how fast is it? Well, so change detection is mainly implemented by Viktor Savkin, core member of the Angular team. And he says change detection is usually very fast. And I like that. It's really like that. So without going into too much detail here, in fact, what Angular does is it generates VM-friendly code for you. So each change detector is not like a single class in Angular that kind of dynamically runs change detection for every component. It's like not one single code that takes care of all components. Actually, what Angular does, it generates classes for you at runtime, which are specifically written for your particular component. And this makes the code super fast. Why? Because it's monomorphic. What does that mean? When you have a change detector that knows about each property and the shape of each object, of your JavaScript objects, this particular shape of a property doesn't change, right? Because it's always the same. Your, your contact component always has this contact object, right? So we know that it's this contact object, and we know the shape of it. If you have a dynamic class or a dynamic change detector that takes care of it, it has to kind of find out what this property is all about. So basically, what Angular does, it creates classes for you at runtime. You don't have to do that. And it generates this monomorphic code, which is super duper cool for VMs, because they can optimize that code. The fact that it's monomorphic allows them to inline your code, and that makes it super fast. So you can basically perform hundreds of thousands of checks during a couple of milliseconds. If you want to learn more about monomorphism, there's a link here. You can read that too. I totally recommend it. Yeah, check that out. So that's basically what makes Angular's change detection super duper fast by default. So here's some facts. The change detection graph is a directed tree. Data always flows from top to bottom, right? That's what it makes it super predictable. We can take a look at the template and we know where the data comes from, right? If we have first name, last name in the expression, we know it comes from that component. It can only come from there. It gets stable after a single pass. So it's faster. We don't have a cycle, right? There's just one pass always. And it generates VM-friendly code for way better performance. It can be up to 10 times faster than Angular 1, depending on your scenario. So this is super cool. This is like way better change detection, but we can do even better. And this is where smarter change detection comes into play. So we can basically tell Angular, so what Angular does by default is it checks every component every single time. It has to do it because, well, maybe something changed in our component, right? So, but if we know that something doesn't change in this particular component, then maybe we can tell Angular to not check this component. So it can just skip that part. We can do that. And it turns out we can do that with immutable data structures or observables, or even both, right? To understand what that means, let's first understand what mutable means. So mutable objects are basically all these objects in JavaScript except for the primitives. So we can change them without changing the reference. What does that mean? So we have another component here. It's a vcard component. Nothing special going on here. It has some data on its constructor, right? It has a child component vcard. And vcard gets this vdata through property binding. So we write this vdata into that vdata component. Yeah? And we know where this data comes from. It comes from our component, because data always flows from top to bottom. And then there is this change data method, which basically kind of mutates this vdata object. So we change this existing object. It's mutable. So here's what that looks like when we visualize that a little bit. So we have this vcard app. It uses a vcard component. And then we know that vdata flows into vcard component. Vdata is this object right here. It has a name, it has email. And we know that when an event is fired, we change that name property, right? So let's say an event is being fired. Change detection kicks in. The name property changed to the different value. Then vcard component checks if the vdata that it gets is the same one as the original one. Well, it turns out it is the same reference. The vdata object that is being passed to that child component is still the same reference, but we changed that property. And that's the reason why Angular still has to check this component, because maybe something changed that particular property, even though the reference is the same. So Angular is conservative about doing that. It always checks every single component every single time. Again, what if we could do something like telling Angular, hey, we know that this particular thing didn't change, so we can skip it. We can do that with immutable objects. And to give you an idea why that helps, I give you some sample code that kind of shows you what immutable objects mean. So immutable objects are basically objects that cannot change. And we don't have this immutability by default in JavaScript, except for the primitives, right? So in order to create immutable objects, you might use some API for that. Maybe you use immutable.js, maybe something else. I have some API for immutables here. So I create an immutable object, and this particular thing takes care of, if I want to do a change to that object, it returns a new one instead of making a change to that reference. So I create an immutable object vdata. I make a change to a property of that object. But instead of changing that same reference, I'm getting a new object back. So I'm actually not changing the original one. I always get a new reference. So when you check those two objects, they're not exactly the same. They would be the same if I would just change that property directly. Does that make sense? Awesome. Okay, so how can we take advantage of this guarantee? Well, making a change always results in a new reference. And we know that components check that, like check if something changed by reference. We can actually reduce the number of checks in our change detection tree. If we tell Angular that this particular component right here should only check when its input property has changed. And we know that a change means a reference change. So that basically means if we use immutable data structures, we know that some certain objects return new references when they change. So if we could tell Angular, hey, please update or please check this component only when the reference changes, then we could actually skip a subtree of the change detector tree. And we can do exactly that. So this is what the vcard component looks like. It only depends on its inputs, the vdata object, right? So now we can tell this particular component, hey, you only need to perform change detection when this input changes. And a change means a new reference. If I use immutable data structures, this is a guarantee. So we set the change detection strategy to onPush. This is how we do it. And that basically tells Angular only run change detection for this component when an input property changes. And again, if we use immutable data structures, a change means a new reference. So we can take advantage of that. So if we go back to this visualization, same thing. We have this vdata. Now an event is being fired. Change detection kicks in. But we don't change this reference. We don't change this object. This can be an immutable object now. This component here realizes, OK, old vdata is still the same as new vdata because we didn't get a new reference. So it can skip the change detection here because we set it to onPush. Pretty cool. So if we take a look at this bigger application, imagine you have hundreds of components. And this one here is set to onPush. When an event is being emitted, change detection only runs in this subtree, but not in the other one, which is, again, way faster than running change detection for all components. I think this is pretty cool. Are you excited about this? Hey, awesome. I give you an even cooler demo. OK, so I have another one here. I click this. Yay, no bugs here. I'm going to close that one. OK, so this is pretty much the same thing, just a bigger component tree. We have 16 components here, 17 actually. You can see some components that are kind of glowing. That just means, hey, you can click me. So there is a click handler registered on that particular component. You can see two components that are set to onPush, right? So when I refresh this page, again, we will see that change detection is being performed for all components because it has to do it initially, right? We want to perform change detection for all components to get the initial view. So I refresh, and we see all are green. Now, if I trigger change detection from now on, we will see that the left subtree is being skipped because component 2 is set to onPush. So I click trigger change detection, and we'll see only the right subtree is being checked. Now, you might wonder why is the second component also turning green. Let me be honest. There's a bug. Right? I'm using a lifecycle callback called afterViewChecked, and I use that to make those components green. Actually, this callback shouldn't be called for this particular component. So it doesn't run change detection. It's just this callback that is being executed, and it shouldn't. So this is just a visual bug at that point. And then also interesting, when I click or when I fire an event from inside this particular subtree here, so I click on component 12. You'll see that also just that particular, the right subtree is being change detected. Another interesting thing is that even if we set a component to onPush, it can happen that there's an event being fired in its subtree. So what does happen then? What Angular does, it still enables change detection for that subtree. So if I click, or if I fire an event from inside a component that is set to onPush, if there's an event being fired, it still runs change detection for this particular tree because there is a change, or there might be a change after this event. Angular is smart enough to find that out. I'll talk to you in a second how that works. And if I would click that component right here, you'll see again that everything's being checked because it's like the very bottom of the change detection tree. I think this is pretty cool, but it gets even better. Just a second. So if you want to see an actual example of an application that uses really immutable data structures with immutable.js, for example, you should totally check out this article by Jürgen van der Moere. He is a great developer, and he helped me out with this talk. Actually, he made the CSS for these nice components, so big shout out to him. Thank you for your help, Jürgen. So you should check out his article on building Minesweeper with Angular 2, and he does that with immutable.js, which is then super fast. So as I mentioned before, there's another data structure that kind of helps out, or that kind of gives us some guarantee when something changed, and that is observables. I won't go too much into how observables work, but so you can trust me if you don't know what observables are. Observables basically, they emit events when a change to an object happened. And that is, again, also a guarantee that tells us, okay, when this particular thing emits an event, we know that there's a change, and only then. So let's take a look at this component here. Imagine we build a shopping cart component, and whenever a user of our e-commerce application takes a product and puts it into the shopping cart, we want to add this little batch with a number that says, you have 3 articles in your shopping cart or something. We could do it something like that, right? So we have this cart batch component. We assume it's set to onPush, and it has this input, which is an observable. So it's a stream of events whenever an item is being added to that cart component, to that shopping cart. So if you want to buy this trousers right here, this event stream will fire an event. And we listen to that event stream, right? We want to update this counter that we have that is set to 0 at the beginning. So whenever someone puts something in there, we increment that counter. Let's take a look at what that looks like when we visualize that. So we have this component tree. They're all gray because we set all of them to onPush, which means basically they only trigger change detection when an input property has changed, right? So now an observable event is being fired somewhere here. So this is basically our cart batch component. We subscribe to that event. We assume that there's an event happening. And now change detection triggers in, right? And always from top to bottom. So it kicks in, and we realize there's actually nothing happening because everything is set to onPush. Even though if we pass this observable object all the way down through inputs to that component down there, the reference of that object hasn't changed, right? It's not an immutable object in that sense. Well, it's immutable because it hasn't changed, actually, but there's nothing that tells Angular, hey, this particular object has changed in terms of references. So there's this event. We trigger change detection, but still, Angular doesn't perform it all the way down because an input property hasn't changed. So the propagation stops. How do we deal with that? There is this super duper smart mechanism. We can actually get an instance of the change detector, or the reference to a change detector of this particular component, like this, so via DI. And then we can use that reference and tell it, hey, listen, when we subscribe to this observable and it emits an event, please mark this component and all the other components, the path basically to the root, to be checked when this turn is done. So we can tell Angular, even though this thing is an observable and the reference doesn't change, we know this thing emits an event. So we can tell Angular, you have to mark the path till root to be checked. And then it runs change detection again. So here's what that looks like. Again, our component tree, everything is set to onPush. The observable event fires. And now we mark the path until root to be checked. Change detection kicks in, and only for this path. Again, this is way faster than checking all the components. So whenever you use immutable data structures or observables, Angular can be way faster. This is super powerful, really. And even though actually what happens once this change detection is being executed it restores the strategies of the components to the original state. So from that point on, they're again kind of disabled until this particular event happens again. This is what I look like. I have a demo on that one too. I think this is the coolest demo from all four. So there's one more even coming. So again, same component tree, all components set to onPush. I refresh the page, you'll see change detection is being performed for all components for the initial view. If I trigger change detection now through like some normal event, it doesn't perform change detection. Again, you see component 1 turns green because of that bug, but it doesn't perform change detection here, right? Now I have this other button which basically says, hey, push an event to component 17. Component 17 is blue here, and this is basically a marker that says this component subscribes to an observable event. So when I click this button, what should happen is that Angular marks this path to root from component 17, and then performs change detection on that one. So I click this button now, and you'll see only that path is being checked. Again, you might wonder why this one turns green, and this one, and also this one here. This is again just due to this bug. It's just the visualization. It doesn't perform change detection on these components. It's really just the fact that it turns green, but it will be fixed soon. There's an issue on that on GitHub. I actually found that bug. Oh yeah. This is what happens when you spend like 2 weeks reading the source code of Angular 2's change detection. Also interesting, when I click component 7 right here, again, actually all of the components are set to onPush, but an event happens inside that subtree. So Angular has to check it. If I click component 7, which also emits an event for the observable, which is being subscribed to here. So it also marks that path, right? And basically, this is the same technique that is being used for this subtree here. So Angular knows that when you have this DOM event, like a click event listener, it basically marks the path to a root for you. This is why it automatically checks this path too. Super smart. Okay, and then one more thing. You have even more control. So you can basically decide when you have a component that has, let's say, we have another component here, and maybe it has some data that is being displayed. It's like some list or something. And it's being updated through a server or whatever, like many times per second. You don't want to execute change detection many times per second, right? Because that slows down your application. It has to check over and over and over again. So that's a moment where you might want to control that yourself. You want to control when change detection is being performed. So what you can do is you can detach your component change detector reference from the entire subtree, and then reattach it when you think it's appropriate. So you have full control over that. I have another demo. So this demo right here is doing exactly that. Component 2 is detached right now. So if I trigger change detection, you will see there's no change detection happening in this subtree right here. I can attach this change detector again if I click this checkbox, and you see everything turns green because now it's again part of the change detection tree. And you can totally do that dynamically, right? You have the full control of that. You can make your apps way faster. Right, I think that's all I got. I think today was a good day. Thank you very much.